In the last lecture, I had stopped at the point of the regenerative amplifier and the problems in amplifying a short pulse. Not really a short pulse, we had elongated the pulse to a nanosecond range, that means a stretched pulse. So, these are the problems in chirped pulse amplification system. So, all these problems have to be looked into carefully and minimized in order to get the best compressed pulse. Okay. So, I will go on to the compression part. That means, I will be in this stage, the compression stage. So, I will be describing how to compress this pulse, which has been amplified. It has been amplified and many problems have cropped up. You have managed some of those problems and some you are ready to live with. Let us see what happens in the compression stage. In the compression stage, again you have two gratings, okay, two gratings which are parallel to each other. This will give you a negative GVD. So, a negative GVD which will be able to compress the pulse. So, here in this picture I show, this is the stretched pulse, okay, it is all these frequencies are stretched out in time. This falls here on this grating and goes out here and then is compressed. Okay. So, in this time, during this time, see here what it shows is the blue light and the green light and the red is here and the blue is here. It would have been completely opposite in case of the stretcher. Okay. So, the compressor is again two gratings, but in this case you do not need these the telescope in between. This is also a stretcher, you do not need that telescope in between. All you have to do is these two sets of gratings reverse the process in which the chirp had taken place. So, you can show it very well in this. This is what happens in a stretcher. You had seen this picture even before. So, this is called a linear chirp. As time goes by, the frequency or the wavelength, the shortest one is here and the longest one there, or it depends. You get, if I write in terms of wavelength, it will be the shortest wavelength and the longest wavelength here, and in terms of frequency it will be the opposite. So, you can describe it however you want. So, we have basically given it a linear chirp. According to time, all my frequencies have been spread out over this time. So, delta, okay, delta lambda basically, all this has been, this much is that delta lambda, all the frequencies that are sitting inside my pulse, and this is the time spread. It has been spread over time, all these frequencies have been spread over time. Now, in a compressor, all I have to do is take the opposite of this. So, I give it a delay. So, I give it a delay of this. Whichever wavelengths were here, all those I give it the maximum delay, and somewhere here, and I give it the shortest delay for this time. So, I have just reversed it. Instead of it going this way linearly, it is going this way. So, who can do this? Who can give this? It will be the compressor which does this job. This has been done in the stretcher, while I have to achieve this in the compressor. So, you have to just go to the opposite way in kind of a stretcher. So, here I wanted to emphasize that the stretcher and the compressor are conjugate of each other, if you can use that word. That is why it is preferred over a fiber. So, whatever is the input pulse here in case of a stretcher here, at the output of the compressor, these should be identical, whether in time or in space. In time, it should go back to the femtosecond range, and in space, it should be a nice little circular structure in the space profile with a Gaussian profile preferably. Okay. So, in space and in time, in both they have you have been able to make these two compatible. That is the whole idea of making a stretcher out of gratings. So, the grating that you have used here and you have used here, suppose it is 1800 lines per mm. Okay. You have to use the same exact same grating lines per mm here also. Then only they will be exactly compatible or exactly conjugate. If you have used 1200 lines per mm grating in case of the stretcher, then you have to use 1200 lines per mm grating in the compressor too. Then only they will be conjugate with each other and you will get the best results. So, in case of it is somewhat like the descriptions are almost similar to that of a stretcher. Now, these are in the parallel mode, okay, not anti-parallel. See, this is called anti-parallel and this is parallel. Okay. So, even in the compressor you have a mirror at the end of one pass and you have a double pass compressor because you get a larger dispersion, a negative dispersion. In case of stretcher it was positive GVD, in case of compressor it is negative GVD. Okay. But then as whichever sign of GVD it is, you are getting more dispersion if you take a double pass. Okay. So, the compressor is also a double pass. So, it passes, here is your input stretch beam, it goes here, it comes out, and then you can keep a mirror here and it goes back and goes back. Okay. So, you have a double pass compressor too. Now, in case of now what happens is, suppose you were to place a stretcher and a compressor one next to the other. You have the input beam, it goes into the stretcher and almost immediately it goes into the compressor. Okay. Then you will always get back that original pulse, temporal pulse which you put in, okay, because they are exactly compatible with each other. No amplifier in between. You put in the pulse into a stretcher and you get it back into the compressor. There will be no aberrations, nothing. You will get that ideal pulse back again. Okay. So, here in the stretcher, you have taken a femtosecond pulse which has become a nanosecond pulse, and in the compressor you go back to a femtosecond pulse. I have not talked about any amplification process in between. Okay. So, here you will get that exact thing. Now, the problem is you have got all these amplifiers in between these two. Because you have these amplifiers in between these two, you have all those aberrations. Not only the aberrations of the amplification process, which is gain narrowing, amplified spontaneous emission and so on. Many other nonlinear effects have also come into the picture because you have increased the output energy. So, those things and plus all these astigmatism and some of the problems of the alignment of the stretcher, all that has to be compensated by this compressor, and it can't do it. Because it cannot do it, you have some limitation on the output pulse that you get here. It may not be exactly, suppose you started off with 70 femtoseconds or say 100 femtoseconds, you will not get back a 100 femtosecond pulse, you may get a 200 femtosecond pulse. So, it is not ideal, all because all those aberrations and problems of a chirp pulse amplification system have come into the picture. Okay. So, the best you can do is do all these alignments meticulously and reduce all those problems in your amplifier. So, quite often what it happens in the real world, in the real system, you have the compressed pulse. Suppose this is my input pulse, it is a nice clean pulse. The compressed pulse may not look as clean as this, it may look something like this, or it may have some more peaks here, and it is not a clean pulse like this. This is all an effect of all those problems that I have discussed before. Because of that, this is what is happening, and this is definitely not what you want. This is in the time domain. Definitely you do not want this, because you are going to focus it onto a target. And remember, all this process had started with the application in ICF, inertial confinement fusion. All these different types of amplification processes, chirp pulse amplification itself was triggered by the need in inertial confinement fusion. So, in that you have this sort of a pulse will not do. It will cause a lot of instabilities in the plasma itself, or in that, or in the target itself. And not only this is in the time domain. I am talking even in the spatial domain. Suppose you don't have a ideal round shape with a Gaussian profile in the spatial realm. A Gaussian profile is always attractive, because when you focus it with a lens or mirrors, concave mirrors, whatever, you focus it to a point, you will always get a very nice tiny spot, which will again have a Gaussian profile, very peaked Gaussian profile. But if it is elliptical, suppose this, it had that ellipticity, suppose it is a bit elliptical like this, okay, it will not become, you will not be able to focus it to that point. You will have something called the airy pattern like this. So, only this part is this tiny spot like this, while you will have rings or patterns, something around that. And you do not want that, because you have to focus it to a tiny spot, and you can eliminate this, physically throw it out, but then you are throwing out even energy along with it. So, all the ideal properties of the seed pulse is not followed through in a chirp pulse amplification system. Okay. But it is the best solution we have in order to get in order to get high peak powers. So, let me go back to that, just describe that original problem of fusion. Remember, we had said I had said here you have this the pellet, and you try to put laser beams from all directions, and then you try to get a compression because of the rocket effect. Okay, all this part gets its plasma filled, and then there is a rocket action, and this is a pellet, and you want to compress it like this. Compress it so that the pellet ignites. It ignites. Okay, and then you have the burn. So ignition and burn, that was the initial thing. But of course, it wasn't successful with that original ICF process. So what researchers have tried out now is, because now you have this high peak power laser and an ultra short pulse, what one can do at this stage, that's what they are thinking, not that they have been successful as yet. At this stage, you bore a hole like this, you make a cone like this, using the same laser, ultra short pulse laser, and here ultra short pulse is required, not a long wavelength nanosecond range laser, which is needed for the compression part. You bore a hole through it and allow this ultra short pulse laser to pass through and ignite the pellet here. The compression is taking place, then you have that ignition. So you have this one more step along with this before the burn take place. That is what the scientists are thinking. They can get sustained fusion process with this in case of inertially confined fusion. That is what they think. Still not yet completely successful, but the process is going on. So this fusion process is one of the very exotic uses of lasers. There are many other uses which I have listed out here. Why do people have interest in high peak power laser? Okay, you can get particle acceleration. Acceleration which takes place in huge accelerators, huge, which occupies a big space in your land, okay, like CERN. Okay, it's a particle accelerator. You can do it in a small, tiny little space in your lab. That has been shown. Particle acceleration takes place with high peak power lasers, ultra short pulse lasers. Okay. So acceleration will take place when you have reached powers of 10 to the power 12 watts per centimeter square. Yeah, I think I've written 12 watts per centimeter square. It's not much. Then you have proton acceleration. This is for electron acceleration. For proton acceleration, you need 10 to the power 20 watts per centimeter square. This is a large order. You have to really extract more energy. But okay, people are thinking in those terms, and some preliminary experiments have been done and people have got success. Nuclear fusion in deuterium is what I described here. Which part of the fusion process can be helped by the use of high peak power lasers and ultra short pulse lasers? Okay, it's called the fast ignition process. Okay. Then you have so many nonlinear optics which gives rise to relativistic electrons, and it's a new field to be studied. In this high energy, extreme electric fields that you can generate with these high peak power lasers. Okay, then you can do time resolved spectroscopy. Obviously time resolved because you have such a short pulse. You can have X-ray generation, phototransmutation, which is very attractive. That means you can transmute atoms from one to the other. Okay. So you can create, say, gold from iron or whatever. You can transmute it. That's an extreme case, I said. So, basically a lot of field in the nuclear physics, accelerator physics, astrophysics, high pressure physics, all this opens up. That is why people have a lot of interest in high peak power lasers, and they continue to endeavor to get the best out of chirped pulse amplification system. Okay. So, these are some of the uses that you need to know, but there is one important problem which you have to understand. I have made a very ultra short pulse, but then do you know how to measure that ultra short pulse? Is there a way you can measure it? Have you thought about that? No photodiode can measure a femtosecond level pulse, because the photodiode processes are not fast enough. If you see in this slide, I have kept a photodiode here and I have kept a photodiode here, and it is able to record something on my oscilloscope. You would say I have measured it, but no, here you have just measured the presence of that pulse. You have not measured its shape. You have not measured its full width half maximum. Okay. How do you record such a pulse? You have to record that. Now, these photodiodes have to be fast. It has to be faster. It should be able to record it faster than a femtosecond. Okay. But how do I do that? I don't have photodiodes which record faster than a femtosecond. And then in fact, when this pulse, say this photodiode, you have detected a pulse, it will generally pass through a cable and something will be recorded on your oscilloscope. Even that cable has to sustain that fast pulse. Can it travel so fast? The cables itself don't sustain more than 300 or 400 picoseconds. Okay. So, now you have in femtosecond scale. So, it will record something, but it will not give you the exact parameters of that pulse. And your oscilloscope itself has limitations. You cannot measure it on a usual oscilloscope. The oscilloscope itself is not fast enough. You will get a pulse which will have some sort of a shape, but this full width half maximum will not be exactly the one that you have. The height of the pulse may not be exactly what you want, but you want that. That is what you want. You want to know the exact temporal shape of the pulse, the time, because that's the crux of the whole problem. When you divide the energy by this time, then only you get that high peak powers. So, if you are unable to measure this time itself, then how do you get those peak powers? How can you give an estimate of that pulse? So, this is a huge problem. Now, how to mitigate this problem? Okay. So, measuring the pulse itself is a job of its own, and people have found ways of doing it. They use light itself to measure light. light itself is used to measure this pulse length, because no other electronics is not going to help you. Electronics is too slow. The photodiode, which is an electronic measuring instrument, the cable that goes to the oscilloscope, an electronic instrument, these are unable to give you any idea of the pulse. So, they did use light. So, what this I will be describing in my next lecture, where it is called an autocorrelator. Autocorrelator, which uses second harmonic generation in order to measure this temporal pulse. So, your learning of second harmonic generation in the nonlinear optic lectures will come useful here.